shows up in your book in the material that we're going to be doing for Unit 4, which is phenolic chemistry. But it's a good place to kind of introduce it here. And then when we go back and look at it later, within the context of an entire set of reactions, it's not like totally new if you've never seen it. So, what we are going to look at here is sort of a little specialized topic, and that is reactions of alpha beta unsaturated carbonyl compounds. So, this is not the most general reaction type. We're looking at systems that look like, as an example, this. We'll do it for a ketone. Something like that. So first we should probably talk about this alpha beta nomenclature. Let's do it over on aldehyde too. So here is an aldehyde. And the way that we're used to numbering the carbons is the aldehyde is number 1, and then you have 2, 3, 4, down the chain. But there's also a way where we're going to be talking about the alpha carbon and the beta carbon and sometimes the gamma carbon. The way that, it's not really a nomenclature system, it's more a designation system. The carbon next to the carbonyl is the alpha carbon. And then you just go down the chain. So there's the beta. Here is the gamma, and here is the delta. It doesn't go much further than that. So there will be a couple times throughout the semester we'll be talking about reaction occurred at the beta carbon. That's what I'm talking about. It's the one that's 2 removed from the carbonyl. Okay, it's not really nomenclature, it's just a way of designating which carbon in relation to the carbonyl. So what we're talking about in alpha beta unsaturated is something like this. We take our aldehyde that we use group. Here's the H, here's the double bond, here's the alpha, here's the beta, there's an unsaturation right there. And they're kind of interesting because they have 2 places nucleophiles can attack. And you can see that if you look at the resonance structure of the compound. So let's go back to the ketone. And we'll do 2 resonance structures for it. One of them, I'm just going to take the carbonyl bond, and I'm going to show the plus on the carbon and the minus on the oxygen. That's the one we've been working on this whole chapter, is this one right here. Where I have O minus, carbon plus. So I'm just taking those electrons and moving them up. Then there's another resonance structure where I can take this pi bond that's alpha beta and I can move it up. That resonance structure looks like this. O minus, double bond there, plus there. So what this means in this system, I have overall, looking at the whole thing, 2 places with delta pluses on them. So I have a carbon with a delta plus in the usual spot, and a carbon with a delta plus way down on the beta carbon. So when I throw in a nucleophile, things can get kind of interesting. The nucleophile can attack here, which we're used to. Grignard's did it, OCH3 did it. But now, it can also attack there. And so things can get a little bit complicated. And so we're going to take a look at a couple of examples. Some nucleophiles very predictably attack at the carbonyl carbon. Some very predictably attack down here. And we'll take a look at what types. And then some, a lot of them, you get mixtures. So let's take a look at the 2 extremes to explain what's going on. First, let's look at the mechanism and discuss what initially happens and then what could happen if you have a specific kind of nucleophile. So, mechanistically, your nucleophile will first attack at the carbonyl carbon. So let's put initial. And that's true all the time. Is that the carbonyl carbon? The reason for that is it's close to the oxygen, it's got a larger delta plus. So whatever nucleophile you put in goes there first. And when it does, I'm going to put some equilibrium arrows here. You have O minus, and then you have nucleophile, and there's your double bond. Now here's where it depends on what kind of nucleophile you have. If your nucleophile is a very reactive nucleophile, so if the nucleophile is very reactive, what that really means is it's not stable by itself, it's not stabilized. It can't be kicked back off. Okay, it's stuck there. And so you get no reverse reaction. The kind of nucleophile that can't be kicked back off, where you go back to this right here, that would be something like a Grignard. So RMGX won't get kicked off, RLI won't get kicked back out, OR minus won't get kicked back out. Things that are pretty reactive. They go on, and there's no way that I'm going to be able to go, oh, I'm just going to kick a Grignard reagent out. That's not going to happen. It's stuck. But what could happen is that it could be kicked off. And if it was kicked off, you go right back to where you were. Okay, so let's say it's not a Grignard, it's something else. It's stabilized somehow. So it could be kicked off. And let's put if the nucleophile is stabilized. And you're back to this. So then you could have the nucleophile attack 1, 2 again. Or it could eventually, it's not such an attractive spot, but it could attack down here on the beta carbon. So you could get attacked there. If that happens, let's move over here. You are going to end up with this. Your nucleophile here, if it attacks the beta carbon, it pushes the pi electrons up, pushes the electrons up onto the oxygen. So you'll end up with this. So that's just attacking the other place. Right? Then when you put it into acid, you do an acid workup. Is there a functional group in that last molecule I drew that looks familiar? There's an enol, right? And what do you know about enols? They're not stable, they tautomerize, right? So this guy is not stable. It's an enol. And it will tautomerize to give you addition there. Now these two additions have slightly different names that hopefully will be familiar to you. The system, to figure out the names, let's number the system. 1, 2, 3, 4. I I'm just numbering the conjugated part of the system. It's not an IUPAC numbering. Okay, we know that we might not necessarily number it like that if we were naming it. This is just starting at one end of the conjugated system and going down to the other with numbers. So they call the addition that gives you this guy right here as a 1,2 addition. That's a 1,2. That's like what a Grignard does. This reaction over here, look at this to figure out its name. What would you call that?
4.
1, 4. Yeah, this is the 1, 4 addition product. And the key thing to figure out which is going to happen is that the initial attack is at the carbonyl carbon, always. Then you get this. And then the real question is, can your nucleophile be spit back out so that it's available to eventually attack the number 4 position? If it can, you'll get some 1,4. If it can't, then you don't get any 1,4. Okay, so let's take a look at nucleophiles. And I'll give you a list of things that are pretty consistent one way or the other. Let's do, actually, I'm going to do something that could be kind of handy. There's a handout on D2L that you guys can get about this. But let's just take a look at a list. Okay, where's the table? Here's the table I want. Okay. So, really reactive nucleophiles. They will do 1, 2. The nucleophiles that are reactive, they will add 1, 2. They will not be kicked off. And so it adds 1, 2, and it's done. So you can see that our list of good nucleophiles are up there. Grignards, alkyl lithiums, OH minus, OR minus, hydride, H minus. And those are going to give you 1, 2 addition. And that is because they are not stable on their own, so once they hit, they stick. If you have stabilized nucleophiles, these are things that on their own, for some reason, have a stability associated with them. So they're things that aren't very reactive. So some examples that we have, let's look at the first 2 for starters, I minus and SH minus. Those are things we kind of classified as good nucleophiles, right? So they tended to attack things. But they, if you remember, were very large. And so they're very polarizable, which made them good nucleophiles. But on the other hand, because they're so large, I minus, kicking it back off and putting an extra electron on it was not a big deal. In terms of how many 53 electrons it had, adding another one, percentage-wise, not a big deal. So it's not tremendously unstable on its own. So you have I minus, RS minus. Enolates are the ones I want to talk about. And they're kind of a foreshadowing of what's going to be coming up in Unit 4. These are the big guys for this topic. Enolates will add 1, 4. They are things that look like this. They are carbon nucleophiles sandwiched in between typically carbonyl groups. So they can look like this, they can look like this. Something like that. They all kind of have this general trend. You can see this. Sometimes you'll see something like that. All of these, the nucleophilic carbon, somewhat nucleophilic, but if it's kicked back off the molecule and it has its minus charge, it can deal with that. Why is that? Resonance in every single case. Yeah, the minus charge is delocalized into both carbonyls here. The minus charge into a carbonyl and into the nitrile. And then the minus charge into the carbonyl and into the nitrile. So in the case of enolates, that negative charge is delocalized, usually several places. So they tend to be on their own fairly stable. So an enolate will hit here, can easily be kicked off, and then eventually is capable of going into the number 4 position. Okay, so next question. These guys. They add 1, 2 first. They get kicked off. And then what you finally see is you see preferentially the 1,4 product, not the 1,2. You see the 1,4. So what you'll see with these stabilized nucleophiles is you see this. And the question is why? Why do you see just the 1,4 and not the 1,2? What's so special about this molecule? There must be something good about it that makes it preferable for it to add right here. Why?
Sterics.
No, not sterics. There's a bond in there that's really strong. It preserves this. It preserves the strong C double bond O, and that's something that's favorable. So what we have is we have a 1,2 product which forms first, and it's fast. And then we have a 1,4 product forms later, and it's a slower reaction. The 1,4 product is more stable. The 1,2 product's less stable. This is sort of sounding like a discussion we had about a month ago. Something that forms fast, forms the less stable product, versus something that forms a little slower and forms the more stable product. Kinetic and thermodynamic, exactly. The 1,2 product is the kinetic product. And the 1,4 is the thermodynamic product. And what changes your ratio now is the nature of the nucleophile. Then a number of them, this is just a smattering, give you mixtures. And if you take a look at the middle grouping there, the mixtures, they're nucleophiles that are pretty good. They're not the most reactive. They aren't really stabilized though. They're just kind of in the middle, so they will give you mixtures. Okay? And we're going to come back and we're going to look at this again in really good detail. It's called a Michael reaction. We'll be taking all sorts of alpha beta unsaturated compounds and we'll be attacking them with various kinds of enolates and see what that forms. And we'll get 1,4 products out of that. All right, so be familiar with this for the test, but it's not going to be a giant portion of your test since we're going to come back and look at it later. I'll get you later. Okay, that's the material for the test right there. So I'm not going to say C13 is what's next. So any questions pertaining to the test? Good.
Your question, the I minus, is it because of Grignard or does that make bromine?
You know, Grignards work best with bromine. I minus, people don't use alkyl iodides and alkyl chlorides really. We tried in lab to use an alkyl chloride and it failed. It wasn't good.
So this wouldn't be a good way to add things in the title position.
You know, it's not for benzene rings. So it wouldn't work, the whole concept of this wouldn't work on a benzene ring.
You can still have a bromine on a benzene and then do a Grignard with that, right?
Absolutely.
Okay.
Yeah, you can have a bromine on a benzene and you can do a Grignard with it. So you can take your bromine on a benzene, instead of waving my hands, let's just write it. There's no problem with doing this. Like that. Okay, it's called phenol Grignard. You can actually buy it in a bottle.
Ooh.
Yeah, you pull it up with a syringe. Yeah.
It's called kinetic thermodynamic, but is a heat still factor?
You know, it's not so much heat, it's the nature of this nucleophile. Yeah, your nucleophile either can be removed, can be kicked back off, or it can't. And that's what's going to dictate which way you're going to go. Alrighty? Okay, now as I mentioned before, if you look at the Unit 3 schedule, we're supposed to start mass spec. But mass spec is an emotionally more difficult topic than C13. C13 is kind of fun. Everyone likes it because it's easy. I'm not going to